All right, welcome guys. Day 2 of quadratics is going to be today. We're going to learn a little bit more about what it means for an expression or a function to be quadratic and how to represent them in a couple different ways. Learned a little bit about how to graph standard form quadratics where there is a middle term. Last lesson, I should say, we didn't have that middle term and it was a little bit easier. Today we're adding a little bit more complexity to it. But you'll see that there's kind of a pattern with these that you'll catch on to pretty quickly. So we're going to jump right into it. This definition was shared last lesson, but for those that need a little bit of a refresher, a quadratic function is any type of a nonlinear function where the rate of change is not consistent or not constant. The graphs of these are those things that we've referred to as parabolas that are a symmetrical curve with either a highest or lowest point corresponding with a maximum or minimum. We introduced the concept of a vertex last week, which again is kind of representative of that highest or lowest point. And there's a lot of application to quadratics, whether it be any type of a projectile that you're dealing with, or stuff that can kind of show some more nonlinear, real-world contextual problems, like a falling object or anything that's projected that eventually you guys get into some higher level math classes, you might be able to do a little bit more with if you have a good understanding of this class. Objectives for today, we want to be able to graph all quadratics. Last lesson, we just focused on the ones where maybe there was simply just an ax squared plus c. Today we're going to add in the bx and talk about how to graph those. Be able to explain key vocab terms like axis of symmetry, vertex, reflection, and y-intercept, and then use these quadratics to represent real-world scenarios. So our standard form, again, we introduced this last lesson, ax squared plus bx plus c. Now this is quite a bit more complex than our standard, linear functions that might look like this, or potentially the linear function that is actually in standard form, ax plus by equals c. These are both linear functions. What makes this a quadratic, as a reminder from last lesson, is that little number 2. The fact that this is ax squared and not just ax makes it a quadratic. And this is considered standard form. A couple more notes just on the shape. Shapes of quadratics are what's known as a parabola or a U-shape. And all parabolas have symmetrical line or have symmetry to them. Okay. That symmetrical line that kind of splits the parabola in half is known as the axis of symmetry. Right? Axis of symmetry essentially represents that symmetrical or fold line. And what that AOS does, axis of symmetry, it intersects the parabola at the vertex, and like I said, it splits the parabola in half. Okay. If we're doing, a fallen object problem or a projectile problem, you know that the axis of symmetry is essentially where that projected item or projected object hits its max point. Okay. Now we're going to introduce you guys to this formula today that can help you find the axis of symmetry. You remember back from our linear function unit, okay, anytime an equation reads x equals some number, let's say x equals 2, what that represents is a vertical line at 2. Okay, so the equation x equals 2 is just a vertical line right here at 2. Well, some really smart guys got together and they figured out that in every parabola that we could find the axis of symmetry by using this simple equation. Okay, opposite b over 2a. Okay, negative b, which is the number that's represented in this spot, over 2 times the a value, which is the number that's in this spot, will find the axis of symmetry really quickly and really easily. Okay? And if you know where the parabola is symmetrical, it actually makes graphing the parabola quite a bit easier. And that's what one of our goals is today, is we can graph all parabolas. All right, so we're going to start by just giving you a quadratic and finding the vertex. Okay, we're going to find where that max or minimum point is. And it's really simple. First thing, identify that AOS. We're going to find where that parabola will be symmetric. And that's given by this formula, opposite b over 2 times the a value. So with this specific quadratic, our b value is the number 4. Our A value is the number 2. So the axis of symmetry is found by using the coordinates or the equation opposite B over 2 times the A. So what we really need to do with this is just plug those numbers in, okay? We would do opposite 4 over 2 times our A value of 2, and that tells us negative 4 over 4. That tells us that this specific parabola will be symmetrical with x equals negative 1, all right? So on a graph, we know that it's going to pass through negative 1. All right. Now, to find the vertex, all we have to do, since the vertex will always be on the axis of symmetry, is we have to take negative 1 and just sub it in to the equation for x. So we would get 2 times negative 1 squared plus 4 times negative 1 minus 3. And when we do the math with all this, we'll find that vertex. Make sure we follow order of operations. This would be negative 1 squared, which is 1, plus negative 4 minus 3. That's going to be 2, let's just simplify this, minus 4 minus 3. And that would tell us, let's see, negative 2 minus 3, that's negative 5, would be the y value when you plug negative 1 in for the x value, right? So the coordinate negative 1, negative 5, then is the vertex of this parabola, okay? So negative 1, negative 5, probably going to occur somewhere right down here. So just based on the equation, based on that axis of symmetry equation, opposite B over 2A, we're able to find where the graph is symmetrical and then plug that x value into the original to figure out exactly where the vertex is. And that tells us a lot. You know, we look at this and the A value is positive, which means that this will be one of those what we call smiley face graphs. So it's probably going to look something like this, okay? Your parabola will. We'll get to that a little bit later, but right now all we're doing is finding vertex. All right, look at this equation. To find the vertex, again, we're going to start with the axis of symmetry, opposite B over 2 times the A. Okay, we look at the equation. A value in this case is basically that number. Well, that's just negative. That means it's negative 1. The B value is going to be this number. Okay, in our case, 6. So to start off by just finding AOS, okay, we're going to do opposite B, so negative 6 over 2 times negative 1. That will be, let's see, negative 6 over negative 2. That simplifies to the number 3. That means that this quadratic would be symmetrical at the x value 3. So again, you can kind of, you can sketch it out. Let's say here's 1, here's 2, here's 3, and here's 4. You know that this thing should be symmetrical with that vertical line. Okay. To figure out the vertex then, we're just going to take 3 and plug it into the equation. So it would be opposite 3 squared plus 6 times 3 plus 4. Make sure we're following order of operations here. This is negative 9 plus 18 plus 4. Now we just have to do the math with it. That's negative 9 increased by 18. That's 9. 9 increased by 4 is going to be a y value of 13. Okay? So we know 3 and then 13, somewhere probably way up here, is going to be the vertex. And again, we learned in the previous lesson, if the A value is negative, like it is right here, you know that it will be one of those frown face graphs. So it might look, maybe I'll try a different color here so it stands out a little bit, but the graph will look something like this. All right. And again, it kind of starts there. It starts with that vertex. don't you guys pause the video, take a moment to try this one on your own, and then I'll work it out for you. Pause the video, see if you can find that vertex. So our equation for axis of symmetry, again, opposite B over 2A. Okay. There's a way to prove how that equation came about. It's just I'm not going to include it in this lesson. If you guys are really curious, we can go through it and practice it, or at least show you exactly where it came from. But right now, we're just going to leave it as is. So let's say that we've got x equals opposite B over 2A. Our A value in this situation is -3. That tells us it's a frown face, or it'll have a relative max. Our B value is +6. So we're going to go opposite 6 over 2 times -3. That tells us AOS. That's -6 over -6, which is equivalent to 1. So our axis of symmetry is x equals 1. We're going to then take that x value, plug it back into the original to find the vertex. Got -3 times 1 squared plus 6 times 1 minus 5. And then do the math here. 1 to the second power would come first because of PEMDAS. 1 squared is 1. Got -3 times 1, which is just -3. 6 times 1 is 6 minus 5. Okay. Remember, in order of operations, addition and subtraction are seen as kind of the same thing, so we just work from left to right. Think temperature, if it's -3, then we increase by 6. Now we're at +3. +3 decreased by 5 is -2. So this will have a vertex of the coordinate 1, -2. Now, when we're actually fully graphing our quadratics today, okay, there's a bit of a process that actually starts to make a lot more sense when you put it into practice. So the first thing we're going to do is find that vertex. We want to know where exactly the quadratic will hit its maximum or minimum point. Okay, that's also going to tell us where the parabola is symmetrical, okay, or where our fold line would be. So we're going to plot and label our vertex, and we'll use a dashed line to show where the axis of symmetry is. Okay? You should be able to tell just based on the equation itself whether it's a min or it's a max. So that's going to be our first thing. Okay, essentially what we just got done practicing. Next thing, we'll find the y-intercept. Remember, this is the value of y when x is 0. And in regards to our standard form quadratic, okay, if x's are zeros, if this is a 0 and this is a 0, essentially the y-intercept is just shown by c. Okay? So kind of similar to slope-intercept form. Okay, it's going to be your constant value. Once we find that y-intercept, we're going to begin reflecting points across the AOS, and I'll show you exactly what that looks like, and then connect our dots with a smooth curve. All right, so a bit of a process. Take some time to write these down, and then we'll actually put it into practice here with a couple examples. All right, first one, we're going to graph this quadratic, -2x squared plus 8x plus 9. So AOS is where we start. Opposite 8 over 2 times -2. Okay. We do the math with that. That's -8 over -4. Tells us that this will be symmetrical with 2. So what I'm going to start with is I'm going to start just with a dashed line right here at 2. All right, I'll label it. This is my AOS. Next thing, I need to find the vertex, and the vertex is just taking 2 and plugging it into the equation. So we got -2 times 2 to the second power plus 8 times 2 plus 9. So this will help me to find that vertex. We do some math here. 2 to the second is 4. 4 times -2 is -8. 8 times 2 is 16. And then plus 9. Fully completing that math, we'll do some temperature math. -8 degrees increased by 16 is +8. +8 plus 9 is 17. Okay? So our vertex is going to be a point that we label. We know that the vertex of this is 2 and then 17, which is right up here. Okay? And based on the equation, we see that A is a negative number. That means we're going to have a frown face. So we know that the graph will look kind of something like this, right? Which I'm not going to complete right now. That's just kind of something to think about. Oops. Go back here. But we know all right, we know where our vertex is. Sorry about that, technical difficulty. Know where our vertex is. The other thing that we're going to plot is we're going to plot the y-intercept. The y-intercept is the number 9. So we know that this should be on our line, the coordinate 0, 9. Now, if you think about it, this is our y-intercept. We know that the red line, the red dashed line, is our symmetrical curve. So we can essentially just reflect the y-intercept 2 units to the axis of symmetry. Another 2 units over should be another point. Because remember, this is a symmetrical curve. And now what you have is you have 3 total coordinates. Okay? I'm going to erase this just for the graph. But we've got the coordinate 0, 9, and we've got its reflection point, which is the coordinate over here, the coordinate 4, 9. So we've just reflected that point over, and now you can see we've got several different points. We've actually got 3. It's actually, probably enough to be able to draw our curve. Okay, so this would be the quadratic that's shown there, -2x squared plus 8x plus 9. All right, it's good to have probably a couple more. You could pick out an x value of 1 and plug that in, and then reflect that across the y-axis. That's another way to do it. But this is probably just fine as well. All right, let's try a couple more here. Again, starts with AOS. All right, we find that axis of symmetry, opposite B over 2 times the A value. So in this situation, our B is -6. So we go +6 over 2 times 3. 6 over 6, this is symmetrical with 1. Okay, so we're going to want to plot that axis of symmetry first. Right, understand that this is going to be a smile face because the A value is positive. So we're going to take 1 and then plug it back into the equation to find the vertex. 3 times 1 to the second minus 6 times 1 plus 2. Do the math with it. 1 to the second is 1. 1 times 3 is 3. Minus 6 plus 2. Some temperature math from left to right. 3 minus 6 is -3. -3 plus 2 is -1. So this is symmetrical, has a minimum value of 1, -1. Okay. Next step, plot the y-intercept. Okay, y-intercept is shown here at +2. We know that 0, 2 is for sure on our line, and also the reflection of 0, 2. We're going to reflect it across the y-intercept, and I'm going to include this point, all right? So reflect that point. You got this one here, and now you kind of have the makings of a pretty decent quadratic, right? To kind of extend this a little bit further, right? Pick out a different value. Let's say that we choose x equals 3 and we plug it into the original equation. So 3 times 3 squared minus 6 times 3 plus 2. And we do the math here. 3 to the second is 9. 9 times 3 is 18 minus 18 plus 2. That's just 2, I believe. So we know that 3, 2. Oh shoot! I just found that point. That's this one right here. Let's try it, everyone. Like 4. So let's say that we chose 4 to plug into it. My bad. we go 3 times 4 to the second minus 6 times 4, and then add 2. Well, that's going to get you, let's see, 16 times 3, that's 48, minus 24 plus 2, that's going to be like 26 units. So if x is 4, 1, 2, 3, and then 4, we go 26 units up. It's going to be way, 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 way up here. All right. I feel like I messed that up somehow. Hopefully you guys get the trend, because I don't really want to start my video over again. I messed something up with the 3. This is what the quadratic is going to look like. I got to figure out what I did wrong there. 3 to the second, that's 9. 9 times 3 is 27. I had 18, that's what it was. So it'd be 27 minus 18. 27 minus 18 is 9. 9 plus 2 is 11. That's what it was. Okay, so 1, 2, 3, and then 11 should be on our graph. That makes way more sense. So this one should be here, and then also its reflected point. 1, 2, 1, 2. This one should also be on your graph. There we go. Now I figured it out. Sometimes you just got to check your work. All right. So have you guys try this one as practice. This one's a little trickier because of the numbers. I want you guys to write it down, see what you can do with it. I'm going to pause the video here. All right, so with this one, guys, we should start with AOS as normal. AOS, again, found by the equation opposite b over 2 times the a. We've got a b value of -2 and a value of 0.25. So our axis of symmetry with this specific quadratic is going to be opposite -2, which is 2, over 2 times 0.25. That's 2 over 0.5, which simplifies to the number 4. So we know that the graph will be symmetrical with x equals 4, which is a vertical line right here. That's our x equals 4. We can plug x equals 4 into the equation to find the vertex. So we've got 0.25 times 4 to the second power minus 2 times 4 plus 4. A lot of using of the number 4. I'm going to throw my microphone on quick so you guys can hear me better. We do the math with that. 4 to the second is 16. 16 times a quarter, or 16 times 0.25 is 4. Another instance of the number 4. Minus 2 times 4, that's 8. Plus 4. 4 minus 8 is -4. -4 plus 4 is 0. Okay? So this will have a y value of 0 if the x of -4 is plugged in. So this one is actually containing a vertex that's right here on the x-axis. Making a video. Sorry. So, yeah. Un momento. All right, that was Mr. Shavi coming in here. So we've got 4 zeros, our vertex. We label it. We know that this is kind of where your quadratic will meet. 0.25 is a positive number, so we know that this will be kind of one of those smile face graphs, and it'll be relatively wide. The next thing we can do is find that y-intercept of 4 and then reflect it. So we know that we'll pass through here, the coordinate 0, 4, and then we reflect that. This is 1, 2, 3, 4 units away from the axis of symmetry. So I'm going to take 4 units from the axis of symmetry, 1, 2, 3, 4, and that's going to be my next coordinate. All right, this will for sure pass through this point and this point, and you can start to kind of get an idea of the shape of this graph. We could plug in a couple others to find them, but generally once you get 3 of them, you're probably in good shape to just draw your parabola. And we're done. All right, a little bit wider of a parabola because of that 0.25. Okay. Again, a lot of stuff we can do with them. We've got a projectile question here. Pedro throws a ball up at a rate of 20 meters per second from an initial height of 2 meters. Height of the ball above the ground can be approximated by the function h equals negative 5t to the second plus 20t plus 2, where t is the amount of time in seconds since the ball's been released. So we're looking for max height that the ball reaches, and when does it reach that max height? So if we again think of this scenario represented on a coordinate grid, you got your vertical axis representing feet, you got your horizontal axis representing time. All right. And what we're essentially looking for is when does it reach its maximum height, which is going to be right here at that vertex point. Okay. And then also, like, not only when does it reach that, but how high. Okay, so we've got the equation that's shown up here is negative 5t to the second plus 20t plus 2. So in that equation, the a value is going to be negative 5. The b value is going to be positive 20. Remember, our equation for axis of symmetry is opposite b over 2 times the a. So with this problem, we're going to throw 20 in for b. So negative, maybe I'll scroll down and get a little bit more space. So we'll be dealing with negative 20 over 2 times the a of negative 5. That's negative 20 over negative 10, or after 2 seconds. Okay, so we know that the axis of symmetry is the equation x equals 2, which tells you about 2 seconds into its flight, it's reaching its maximum height. Right? That's only part of the question, right? We also need to find the maximum height that the ball reaches, which is essentially just saying, all right, if 2 is my time, what value would be my height? Well, all I have to do is plug that into the original equation that we had, negative 5 t to the second plus 20t plus 2. If I substitute 2 seconds in for time, at negative 5 times 2 squared plus 20 times 2 plus 2. I could actually use my microphone and turn it on. I hope you guys have been able to hear me. Do the math of this. 2 to the second power is 4. 4 multiplied by negative 5 plus 40 plus 2. So this is negative 20 plus 40 plus 2. That's going to be, I think, if I do my math in my head correctly, 22 feet. Actually, I think we're dealing with meters. 22 meters. All right. So after 2 seconds, the ball will be 20 meters in the air. All right. A lot that you guys can understand and make sense of with quadratics. It'll take this ball about 4 seconds to land. All right, it's got a 4-second hang time. You look back at the equation. If you think about what this number even represents, given the context, that 2 might represent, forget we're dealing with meters, but not 2 feet, but it essentially represents the height the ball is left, or is thrown from. So it's thrown from 2 meters height. It reaches its max height after 2 seconds at 20 meters. Again, we just pulled a lot of that from the same problem. Okay. All right. Got a golf question. Again, we can throw a lot of different things at you when it comes to quadratics. I want you guys to pause the video and think of this. All right, and then we'll attempt to answer these on the next slide. So our equation was negative 5.4t squared plus 34.4t. That's our original equation. The first question just says graph it. Essentially, graph the equation and what do portions of the graph where h is greater than 0 represent, given the context? What does the end behavior of the graph represent? So to graph this, first thing we're going to find is AOS. This is equal to the height. So let's start with axis of symmetry. That's opposite b over 2a. In this case, b is 34.4. So negative 34.4 over 2 times negative 5.4. That's negative 34.4 over, what would this be, negative 10.8. We do the math with that. I'm going to just ask Siri, hey Siri, what's negative 34.4 divided by negative 10.8? Hey Siri, what's negative 34.4 divided by negative 10.8?
Negative 34.4 divided by negative 10.8 is about 3.1851.
All right, so about 3.18. Let's round this to 3.2. So our AOS is going to be 3.2. All right, we're hitting the ball here at about 1, 2, 3, and then 0.2 is going to be where this ball reaches its max height. So right along this line is our axis of symmetry. We can label it 3.2. Right. Next thing we'll do is find the vertex to figure out how high the ball actually travels. So we've got negative 5.4 times 3.2 to the second plus 34.4 times 3.2. Work's kind of shrinking together here, but this is just the attempt to find the vertex. So let's do our math here. 3.2 to the second. I just use my big boy calculator instead of my phone. So 3.2 raised to the second power is 10.24. That number multiplied by negative 5.4 is going to get me negative 55.29. So I'm going to round that, negative 55.3. Plus, if you take 34.4 and multiply it by 3.2, that gets you 110.08. Okay, maybe we round that to 110.1. Now just do the math here. 110.1 plus negative 55.3 gets us a height of about 54 feet, 54.8 feet. All right, so this golf ball, and we got our golfer guy down here. All right, he's got his club. He's hitting his golf ball. It's going to reach its max height at 54.8 feet. So here's 40, 45, 50, and 4.8 is probably, I'm gonna estimate it here, but it's going to be about here. So it starts off here. Okay. Now you think about AOS. In this situation, this is 1, 2, 3.2 units away from the axis of symmetry. So we would know that this is going to be about 3.2 units away from there. So if you add 3.2 and 3.2, that's 6.4. So this ball should land after about 6.4 feet, or sorry, 6.4 seconds. 1, 2, 3 and a quarter. Yeah, right about there. All right, so ball's going to take off, reach its maximum height, come down. And if you look back to that question here, the graph the equation, what do portions of the graph where h is greater than 0 represent? Okay, so basically when h is greater than 0, remember h is over here. When h is greater than 0, that's the flight of the ball. All right, that's the flight of the ball, and how high it actually gets. What does the end behavior of the graph represent? Right? this end behavior is saying essentially that after about 6.4 seconds, the ball's going to land. It doesn't tell you that it's going 6.4 yards, meters, feet. It just says it's going to land after 6.4 seconds. That's how long the ball will be in flight. Okay. What's the maximum height? Well, we figured that out. All right, we figured that out. 54.8 was our vertex here. So 3.2 comma 54.8 is the vertex. And the last question that was asked there was how long did it take for the ball to land? Well, it's about 2 times the axis of symmetry. Right, so the ball hits its maximum height at 3.2. It's going to land about 6.4 seconds past. Right, a lot of math involved. Hopefully it's making some sense to you guys. We're going to take the time to write about the terms that you've heard that are new today, the terms that you've heard or used before, so stuff that's new, and then one thing you found confusing about the lesson. I want you guys to take that time to do so. I think it's good practice to write about what you're learning, especially when you're learning new things. And that'll be it for today. You guys will have your daily work, obviously, but in terms of the lesson portion, we're all done. Thanks for listening, guys.